Okay, I did see last night when I was reading at home a couple of announcements. I couldn't print them out there. I wasn't hooked up to any printer from my laptop, so I was going to try to do it this morning, but I got, like I said, caught in the email vortex. So I was going to go into email to print them out and never even got to them. We had a department chair meeting on last Friday, and they told us we had to correct a bunch of courses that we corrected before, but they didn't bother to do so. So we had to do that immediately. We had to do degree plans. I can't think what they call it. Term by term for all the majors, and of course I got umpteen engineering majors, math and physics and things. So I had to print off all those STARS agreements for every one of those. And then when I was trying to find the email I was looking for, then they wanted us to update the website. So they just keep throwing things on top of us, and of course they had tons of things wrong on the website. So anyway, didn't get here in time. So let's go from the current slide. All right. Now, we've already done example 4, and we did example 5, but this was where we left off last time. First, are there any questions for anything we've done so far? None? Okay. Then let's move on to solids with known cross-sections. This is on Chapter 7, Application of Integration, 7.2 Volume, the disk method, and Ryan decided to show up today. Okay.
My shirt.
Huh?
My shirt.
What's that?
Nice shirt.
Oh, thank you so much. Okay. It was a gift. Okay. And 7.2 is volume, the disk method, and we're picking up with solids with known cross-sections, okay, which is sort of a nebulous kind of title, but let's see what they're talking about. With the disk method, you can find the volume of solid having a circular cross-section area, that's what we've been doing so far, whose area is pi r squared, where r is the radius of that section. That method can be generalized to solids of any shape as long as you know a formula for the area of an arbitrary cross-section of that solid. Some common cross-sections are squares. Yeah, we know those areas. Rectangles, we know those areas. Triangles, yeah, we know pretty much those areas. Semicircles, yeah, if we know circles, we know semicircles. Trapezoids, yeah. Hopefully we know those as well, okay? So let's see what they're talking about. So let's say we have, didn't erase the word good. Well, for cross-section areas, A of x taken perpendicular to the x-axis, okay, the volume would be the integral from A to B, that's wherever on the x-axis you start A, to wherever on the x-axis you end B, and, okay, here's the x-axis here. So let's say we have an area here. This is not one of those areas that we fit the bill all that well, or it doesn't appear to be, okay? But if you're talking about this cross-section here, okay, and you're trying to do the volume of this, if you know the area of this cross-section here, the one that's sort of tannish, okay, that would be, looks like it's flat on the bottom, this side and that side, but it looks like it's curved here. Now, if you know that curve, then you might be able to handle this, okay? But this is not a particularly good example for what they were saying earlier. That's something, just looking at it, I don't know what that cross-sectional area is. But if you did know what the cross-sectional area was there, then multiply that by dx and integrate from A to B. X equal A is where it begins, and X equal B is where it ends. Okay? You would start the cross-section there, A, and then move it right across. Or for cross-section area A of Y, you know some area here. Now that makes a lot more sense. This one, I don't know this area. This one looks like a rectangle to me, okay? So if you can figure out the length of the rectangle and the width of the rectangle, then the dy is that. So this same shape here, this is something I don't know. This is something I do know. If I can figure out an equation for the height here, I think I can, because I must have the equation for that curve there. So that would give me the height of the curve at any y. And the width, if I know the x value here and here, then we're going to integrate from y is equal to c, which is back here, to y is equal to d, which is up here, and do the cross section. The thickness of that is your dy. So this one looks like one I could do. This one, I'm not sure I could do that unless I knew for sure this formula and that was an easy formula to do. I don't think that would be the case. This one, much easier to go that route. Same volume, that's the route I would go. Say again? Page number. This is page 459, chapter 7, application of integration, 7.2, volume, the disk method, and even Fred showed up today. Okay, good deal. All right. Y'all like these one-day-a-week classes, don't you? Okay, never mind. Don't answer that question. Okay. So, and this is page 459. Just at the bottom of the page, I'm getting ready to turn to 460. Okay? 460 is example 6. Okay? It says here, find the volume of the solid shown here in this figure, 725. The base of the solid is the region bounded by the lines. That's the base down here. F of x is 1 minus x over 2. Okay? 1 minus x over 2. G of x is minus 1 plus x over 2. And x equals 0 is the back plane back here. Okay? So, let's see if this is making sense. This is f of x, function of x. When x is 0, of course, that would be back here. This one would be 1. And it has a slope here of minus 1/2 x. Okay? You have to take a look at it this way. Okay? That's the slope of minus 1/2 x. Take this plane and stand it upright, and it intersects up here at 1 and intersects x at 2 down here. So that slope would be change of y 1 over change of x 2. So that's minus 1 over 2. Okay, the g of x, this line here, again, stand it up like this. It has a minus 1 as the y-intercept, and it has a plus because now it's going up like this, going from minus 1 to 2 here. So change of y would be 1 and change of x 2. So that's a positive there because when you turn this upward, that's going up, this is coming down. So those two lines make sense. And x equals 0, that's the plane back here. All right. Now, that's what they tell you. They don't tell you anything about this right here. Okay? They just draw it for you. So you don't, make it kind of hard to figure here. Didn't read the last sentence. The cross sections perpendicular to the x-axis are equilateral triangles. That tells you what you need to know here. Okay? So the cross sections are equilateral triangles. We can figure that area. The length of this has to be the same as that length and that length. equilateral is equal lengths on each side. Okay, so that's then gives you the rest of this. All right, so what you have to do is figure out the area of this particular triangle here. Now, you've come some distance x from the origin here, and whatever distance x you've come here, the length of this side is y minus f of x minus g of x. Okay, this is the one on top, this is the one on bottom. Okay, so it's this minus that, and here we have Josh, right, okay. Is your other swimmer coming?
I don't know. I woke up late. I didn't even get to make it.
Oh, you didn't even make it to swimming, huh?
I
Okay.
was disappointed too.
All right. Oh, he made it over. Okay. Waterlogged OED. Okay. Dawson's here. Top part of the alphabet doing quite well. The bottom part is a little sparse. Okay. All right. So here we have the length of this triangle. Okay. Length of this side is F minus G. Okay. This minus that. Well, let's see what that would be. That would be 1 minus a minus 1 would be 2. Minus this minus that would be minus x. Because minus x over 2 and minus another x over 2 would be minus x. So it would be 2 minus x would be the length of that side. Okay, if you know that, okay, you know, then let's draw a representative equilateral triangle. Okay.
How did you determine the side?
So what?
How did you determine the side?
The sign, S-I-G?
Side. Side. Like
Side.
Yeah.
Okay. You're going from this line to that line. This line is your f of x. This line is your g of x.
Okay.
So the length of that side down there is going to be f minus g. And that's what they showed here. It's this minus that. So this is the length. There's the width. Okay? Now, this is showing the triangular base, which is not a particularly helpful deal here. Okay? You know that your integration is going to go from x equals 0 to x equals 2. No problem there, because you got a dx here. So, but this does give you this length. Okay? What you need to focus on is the area of this triangle. Well, you know its base, and it's 1/2. The area of this is 1/2 the base times the height. Well, you need to also know the height. Let's see if they do anything there. I don't see that they do. Okay. For an equilateral triangle here, let me get my pen set up. Okay. It didn't set up, did it? There we go. Okay. Here was the base of this triangle here. Okay. Here's the x-axis coming through the middle of it. And this is going from f on this side, which is 1 minus x over 2, to f on this side, g on this side, which is minus 1, plus x over 2. Okay? So that's the length of that. We already determined that. That total length is this minus that, which is 2 minus x. We already determined that. That's the length of this line here for whatever x you are, from x equals 0 when that length is 2 to x equal 2 when the length is 0. Okay? So that's the length of that. Now, what we're interested in is an equilateral triangle, so this is also 2 minus x, and this is also 2 minus x. They've got to be, right? Equilateral triangle. Well, what is the height of that? Well, an equilateral triangle is also an equal angular triangle, right? And what are those angles? 60, 60, and this one, total one, is 60, which makes each of these smaller ones, see that line bisects it,
Oh, 30.
30. So that's 30 here and 30 there. Okay? So now I think we have enough to figure out what the height is. That's what we're interested in. What's the height of this triangle? Okay? Well, there's a couple ways you can do it. This is a 30, 60, 90 triangle, right? This is the short side, that's the long side. Anyone know what the length of the long side of the 30, 60, 90 triangle is? Oh my, we have to remember trig. No, heaven forbid. Okay, let's think of that. Let's do a simpler one. Let's do one here, one here. That would make this 2, this 2. Okay. So this length is 1, that length is 2. All right. Maya's here. All right. Top part of the alphabet doing quite well. The bottom part is 1 out of 3. Okay. Now, does that ring any bells? What we're interested in is this length right here. This is 1, that's 2.
So 1 as well, isn't it?
Second?
It's 1 as well, isn't it? Is it 1? Is it 1?
Okay, I don't think that's 1. Because 1 squared plus 1 squared would be 2, and that would be, the hypotenuse would then be the square root of 2. That would be a 45, 45, 90. Oh my. Oh, it makes it hurt to think this hard, right?
Oh, it's root 3.
Ah, it's what?
Root 3.
Root 3, you got it. That's root 3. It's root 3 times the short side. Well, the short side is exactly half of the length, okay? So this height here is root 3 over 2 times 2 minus x. It's a weird way to write it, but that's what it is. Because half of this length, half of that is 1, half of that is 1, and this would be root 3 times half of this. So put the root 3 over 2 times that. So there's the height. We know the base, and we got 1/2 the base times the height. Remember, that's the area of a triangle, right? Whew, so let's get it again. So that'd be 1/2 of 1/2, so that'd be 1/4, or root 3 over 4 times the base times the height times 2 minus x squared. Make sense? Okay? Okay? There was a reason for that. The area of a triangle is 1/2 the base times the height, right? So 1/1/2 is out there. The base is this. There's one of those. The height is this. There's the other 1/2, right? So that takes it over 4, root 3, and then there's the other factor there. Okay? So the area of a triangle is 1/2 the base times the height. Okay? And we just determined that the 1/2, the base was 2 minus x, and the height was this thing here, root 3 over 2 times 2 minus x. Okay, and when you combine those together, you get root 3 over 4, combining those two, times 2 minus x squared. Right? Yay or nay? Say the yay with enthusiasm, okay? Yay! Okay. We got it, right? Boy, Nick Saban would be very upset if you were his cheering section. I mean, never mind. Just kidding. Okay, not too much. Okay, so there is the area of this little triangle here, anywhere there along the axis. So what's our volume? Find the volume. That's what we're looking for. Let me erase some of the extra stuff here. So I'm going to erase all this that I just wrote, except this. All right, this is the area of that triangular section there. The thickness of that is, of course, dx. Okay, so let me erase the rest of this. Don't think we need that anymore. You know where we got it. You can go back and reproduce it if you need it. All right. Now, what is the volume then? That's what we're looking for. The volume is, anybody? Integral from? Okay, and what's your A and your B here? Okay, what is your D here? What D are we going to have at the end? What is your D right there? dx. So what's your x going from? It's going from 0 to 2. You always match your limits with what your D is, what your incremental part is. Okay? What next? Okay, that's your area. Here's your area, there's the thickness. You're summing all those up. That gives you a volume. Area times the thickness gives you the volume. So this is all you're doing. So put the root 3 over 4 out front, and let's go on and square that. What would that give you? I hope it's not that hard. Say again? Square that. Not that bad, is it? Okay, there is an x squared in it. What else? Square binomial? You could do it this way. 2 minus x times 2 minus x. That's what it means to square something, right? Multiply it by itself. And what does that give you? Ooh! What was that again? 4 minus 4x plus x squared. Okay? The easy way, square the first, 4, twice the product of the 2. 2 times negative x is minus 2x. Double that, you get minus 4x, then square the last. Okay. Now, can we integrate that? That would be root 3 over 4. And what's the antiderivative of 4? 4x. Antiderivative of minus 4x. 2x squared. Is that right? Yeah. Yeah. Because when you take a derivative of it, you get 4x. Right. Okay, next. Plus x cubed over 3. Evaluate that from 0 to 2. All right. That's root 3 over 4. Okay, what do you get when you plug in a 2? 8 minus 8. That's easy. Plus 8/3. And I think I'll plug in the 0 part. Okay, done for you. Okay. These go to 0, of course. Okay. And that gives you root 3, well, let's do 4 will go into 8 twice, so this will be 2 root 3 over 3. Let's hope that's what they get for their answer. Oh my goodness, look at that. They got it right. Okay? 2 root 3 over 3. Does that make sense? All right. The problem didn't make lots of sense until I read this down here. The cross-section perpendicular to the axis of equilateral triangle. Once we knew that, yeah, we can then figure the area of that equilateral triangle multiplied by your thickness, which is dx, you get the volume, integrate those volumes from 0 to 2. Got it? Fine. But the geometry of it, the setting up the problem, that's the hard part. The calculus, that's the easy part, okay? Just do the antiderivative. Let's see how they did it, okay? The base and the area of each triangular cross-section are as follows. The base is the f function, that's the side over there, minus the g function, that's the side over here. We verified both of those made sense. So that would be 1 minus the minus 1, that would be 1 plus 1 is 2. And then minus x over 2 minus another x over 2 would be minus x. So there's the length of the base. Okay? The area, they just pop up with root 3 over 4 times the base squared. Thank you very much for explaining where that came from. Okay?
Why did we subtract?
What's that?
Why did we subtract?
Okay? Let's go back to our picture here. The length of the base, okay, here was y is equal to f of x, right? Here is y is equal to g of x here. The base is the distance between those two, f minus g. F minus g. Make sense? Okay. All right. What if I had a tape measure across the floor here? Okay, and here was 3 feet right here, and here was 7 feet right here. And I said, what's the distance between there and there? This minus that. Okay, that gives you the length, right? Okay, and PR is here. All right, just missing one. Very last on the alphabet, but all the first part of the alphabet. All right, so that answers that question for you. Length of a length is one end minus the other end. Okay, and they gave us the ends. So that's where they got the length of the base. Now, we went through quite a bit to get to that, but that's exactly what we came to, is root 3 over 4 times the base squared. Now, that's not some formula that you would automatically memorize, because this is a very specialized case, but in this case, it is absolutely correct. We worked it out and got it. Okay? Then your a of x is root 3 over 4 times 2 minus x, which is the length of the base, squared. Okay? And that's what we put in our integral. The volume would then be from a to b, as y'all were saying, a of x dx. X ranges from 0 to 2, so the a is 0, the b is 2. Volume is the integral from 0 to 2 of root 3 over 4 times 2 minus x squared dx. I pulled the root 3 over 4 outside, which they ultimately did, and then they did it this way, which is perfectly fine as long as you know what they're doing here. They did the antiderivative of this entity here, squared, would be that entity cubed over 3, but times the chain rule in reverse of this would be a minus. So that's where the minus out here comes from. I thought of doing it this way. I said that would be way too confusing. I don't know. Maybe it's not. That's how they chose to do it. And bizarre, but true. Okay? It really works. Okay? and then you plug in and see. So if you plug in a 2 here, you get 0. Okay? Then you plug in a 0 here, you get 2 cubed over 3 times root 3, and 2 cubed is 8 over 3 times 4. But you're minusing, so the minus of minus becomes a plus, and you get 8 root 3 over 4. 4 goes 8 twice, so you get 2 root 3 over 3. That's the easiest way to express it. All right. I think they chose sort of a bizarre way to do it, but it works. Okay? I think that's the last slide. They left off example 7. Any questions on 6 before we leave it? Okay? Example 7. Prove that the volume of a pyramid with a square base is V is equal to 1/3 HB. Okay? The volume of a pyramid with a square base, I'm going to put B squared. That's not accurate, but that means a square base. That this is 1/3. I usually see capital BH. They do HB. I don't know why. Where B is the area of the base. Now, frankly, that's the volume of any pyramid. Okay, 1/3 the area of the the volume of the pyramid. 1/3 the area of the base times the height. It certainly works for a square, but it works for any kind of a pyramid as well. Okay, so that's the volume. Now it says prove this, where H is the height of the pyramid and B is the area of the base. We know the area of the base is a square, so we could write this as 1/3 S squared H. Okay? Now we have a problem here in that there's no it looks like we have 2 variables to deal with, okay? We really don't, in a sense, because if you're, I hate to try to draw this, but I will try to draw it. And I also hate they drew it this way, but I'll try to draw it the same way they did. Here's the x-axis, here's the y-axis. We know it goes up h on the y-axis, okay? That's how far it goes on the y-axis, okay? Now they do their sides as b, little b, rather than s. I sort of prefer s, but if you like the little b, we'll go with the little b, okay? So, it has a square base. Let's see if I can kind of draw this. This is not easy to draw. Okay, let's pretend that's a square. Okay? Now, in pretending it's a square, and if I call them S, they call them B, if this length here is B, okay, then this is B over 2, and this is B over 2. This is B over 2. This is B over 2. They don't look like they're equal. This is B over 2. It's square. B over 2. And I don't know what this was. Let's just call this B, okay? Because there's not really a line that cuts through there. Okay. So this is B, okay? And this is B back here too. All right. All right. Then the pyramid goes up from each corner. Rather ugly, but you get the general idea. So any cross-sectional area here, guess what? We're going to do dy's. So let's do a little cross-sectional area here of a dy. Okay, and that's going to be a square, right? All right. Now, let's imagine this triangle right here. The height is h. The length is b over 2. I've got it way too long, probably. And then you're coming down the middle of that side there, and we need to determine, well, we don't really need anything there, I don't think. Perhaps we do. So this is b over 2 right here. So I did need this as b over 2. Okay? Yeah, that's where I should have put this as b over 2 here. Okay. Now, this side here is the hypotenuse, which is the square root of h squared plus b squared over 4. Does everybody buy that? I don't know if you need to buy it, but you could say, rewrite this as the square root of 4h squared plus b squared over 4. And then pull out the 4, which would then be the square root of 4h squared plus, plus b squared over 2. Okay, because here that's under the radical, here it's outside. Okay. Don't know if that's useful, but that's that slant side there. Okay. Now, what that does give you, though, is a way to express h as a function of b, I think. We may or may not use that. Let's see. All right. As you go up here, and this is your dy, by the way, is the thickness of that side there, of the slice, okay? As you go up here, your height right here is y, okay? This is your height y. So the height that's left up here is h minus y, right? Okay. Now, this h minus y is to they introduce a new variable here, b prime, which is the length of this little side here, b prime, okay? That's been getting shorter as you go up too. And the ratio for this triangle here, down here, this is b over 2, this is h here, so the ratio of h to b over 2 is the same as the ratio of h minus y to this b prime, which is the length of that side there. Let me make sure that, yeah, that's what we've got. That is the no, I think this is h is to b, not b over 2. If they're using b prime as that length, then it's b, not, okay. Now, so what we need to do is to, since this b prime was sort of a made up thing anyway, that is, it's the length of that side, okay? So that is important. So let's solve for b prime. So b prime is equal to h minus y b over h. Okay. If you do the cross product here, hb prime is equal to b times h minus y, and then divide by the h. Okay. That gives you the length of a side of this one here. So the area of that base would be this thing squared. Okay. So this would be b prime squared would be b squared over h squared times h minus y squared. Okay? Now h is fixed. H is not a variable here. H is fixed. And actually the b is fixed too. So that's the area of the base, which is what we're looking for. Y is the only variable here, so you multiply that by dy. Okay? And that gives you the integral from 0 to h. Okay? So this is the volume. So let's write it up here. V is equal to the b squared over h squared comes out front. And you have the integral from 0 to h of, let's go on and square that. What would h minus y squared be? We just did it, didn't we? Help me, somebody. H minus y squared. You could do it the way they did it if you wanted to. I like it this way better. It doesn't matter. What would that be? H minus y squared. H squared minus 2hy plus y squared dy, because that's the thickness of the base. So let's do it. That would be b squared over h squared. Those are constants. And then the antiderivative of h squared, that's a constant, would be antiderivative of h squared would be, help me, it's a constant, h squared, integrating with respect to y, that's just a constant. Y. Okay, that's your variable. Okay, minus the antiderivative of 2hy. Help me. Okay. What if we did it h times 2y? What's the antiderivative of 2y? Y squared. So this would be h y squared. And then finally we have a plus. What's the antiderivative of y cubed? Y squared. Y cubed over 3. Okay, and we're going from 0 to h. All right. Now, I'm going to erase some stuff here that we didn't need. That was superfluous, unnecessary. That got us nowhere. Okay. So, let's see what we got now. This volume is equal to b squared over h squared times, now when you plug in an h for the y, what do you get? H cubed minus h cubed plus h cubed over 3. Okay? And when you multiply these together, these of course go out. The h squared will go into h cubed h time, and what do you have? You have 1/3 b squared h, which is the b squared is your base. Okay, I called it s squared. They called it little b squared. So we have just proven what they said to prove. 1/3 h times the base. All right. That was so much fun, wasn't it? All right. Homework exercises 7.2. Either 5 or 7, they're both at Calc Chat. 5's at Calc View. Either 9 or 11, they're both at Calc Chat. 9's at Calc View. Either 13 or 15, they're both at Calc Chat. 13's at Calc View. 17 or 19, they're both at Calc Chat. 17's at Calc View. 21 or 23, they're both at Calc Chat. 23's at Calc View. Any of the odds, 25 to 31, they're all at Calc Chat. 33 or 35's at Calc Chat. 37 or 39, Calc Chat, with 37 being at Calc View. Any of the odds, 41 to 47, they're all at Calc Chat. 49 or 51, they're both at Calc Chat. 53, you can explore doing that if you'd like. It's up to you. It should be at Calc Chat. 55 should be at Calc Chat. 57 should be at Calc Chat. And then any of the odds, 59 through 67 should be at Calc Chat. 69 should be at Calc Chat. You can think about doing 71 if you'd like. That should be at Calc Chat. 73 or 75 should be at Calc Chat. And boy, 75 looks like a bear and a half, but you can investigate that if you'd like. Okay? And then 77 should be at Calc Chat. All right. That's using the disk method even when you have things that are not rotated around an axis, but things that you know the cross-sectional areas, or you could determine that. So disk method works for that as well. Now we move on to 7.3. Sometimes the disk method just doesn't work too well. And then we can use a different method called the shell method. Okay. So these are still applications of integration. 7.3 is determining volume, this time using a shell method rather than a disk method. So we'll find the volume of a solid or revolution using the shell method and compare the uses of disk method and shell method. So here's the shell method. All right. An alternative method of finding volume of a solid of revolution is called the shell method because it uses cylindrical shells. Now, a comparison of the advantages of disk and shell methods will be given later in the section. Right now, we're just going to deal with the shell and how we develop it. Okay? Let's do a representative rectangle shown here. Here's a rectangle. The thickness is W here. The length is H. There's a rectangle of thickness W of length H. Okay. Now, so that gives you the area of this little rectangular piece here. What we're going to do is rotate that around the axis. Okay? You don't list which axis this is. It really doesn't matter. It's just your axis of rotation. Okay? Now, the inner part radius of that is P minus W over 2 because start here. P is the center of this. From the axis to the center, that's your P. So P minus W over 2 would be the lower radius, and P plus W over 2 would be the upper radius. frankly, I see not a lot of reason to do this, but that's how they're choosing to do it. Okay? It's going to be far easier to just come up with a conclusion at the end without remembering those, but we'll go with it. Where P is the distance between the axis of revolution and the center of the rectangle. Okay? When that rectangle is revolved around the axis of revolution, it forms a cylindrical shell or a tube of thickness W. Okay? So to find the volume of that shell, consider two cylinders. The radius of the larger cylinder corresponds to the outer radius of the shell, that's the P plus 2, P plus W over 2. And the radius of the smaller cylinder corresponds to the inner radius of the shell, which is P minus W over 2. Because P is the average radius of the shell, you know that the outer radius is this, and the inner radius is that. That's what we saw in the picture, and that's what I just said. Okay? Again, rather bizarre way of doing it, but it's okay. So the volume of the shell is the volume of the cylinder on the outside minus the volume of the hole on the inside. Okay? Which would be pi times this radius, P plus W over 2 squared times H. That's the volume of the cylinder, the outer cylinder. Okay? It's the area is pi times the radius of that, which is this thing here, squared, pi r squared times H, okay, which is the height length of that cylinder, minus pi times this is the hole that's on the inside. Subtracting that off, that would be that. Now, if you do the math, this would be P squared plus PW, because twice the product of these two, plus PW, plus W squared over 4. Okay, so P squared plus PW plus W squared over 4 times pi times H. Minus, and this would be P squared minus PW, okay, squared, PW, plus W squared over 4 times H. Now, the pi P squared H, this is a plus over here and a minus over here, they disappear. The pi times W squared over 4 times H, and just remember when you square it, that's plus, those go away. All that you have left is pi times PW H minus a minus pi times PW H, which is plus, so that gives you 2 pi PWH. Why they changed the order, I don't know. Okay, so what does this give you? 2 pi times the average radius, P, times the height, times the thickness. Okay? And it says you can use that formula to find the volume of a solid of revolution. 2 pi times the average radius times the height times the thickness. Okay. Now, let's go back here to this picture here. All right? Now, this is how I would do this. I wanted to show you how they did it. What I would do is take me some scissors and cut a straight line right down the middle there, wherever you wanted to do it. Maybe right there, where that is, right there. And lay it flat, right? What do you have there? A rectangle. What is the length of that rectangle? Well, depends on what you call length and width. One dimension is the H, right? Okay, so got that. The other one is the circumference of that. And since we're using P as the average, that's 2P, which is your radius, 2 pi P, right? 2 pi R is your circumference, right? Everybody remember that? Circumference of a circle is 2 pi radius. The radius is P, so 2 pi P times H times thickness W. Okay? You even need that? Yeah. That is the length times width times the thickness is W. 2 pi P H W. Two pi P H W. Why go through all the inner and outer radius and stuff like this? Why don't you just cut it, lay it out? There is your thickness, W. 2 pi P is your circumference, H is your length, and W is your thickness. That's it. I saw no reason to go through all this stuff. It works. It certainly does. It's fine, but it's just as good to lay it out flat and do it that way. It's so much simpler to do. So that's how I always look at these shell methods. I don't think inner and outer radius and that kind of stuff. Just lay it flat. Okay. So for instance, the plane region in this one, figure 728, is revolved about a line to form the indicated solid. Okay? So what we have is this triangle here, this light blue triangle. Forget about that in there for now. And you're revolving this around this axis, about the line. Let's call it the line, which is the axis of revolution here. Okay? Now, if you tried to do this using the disk method, that might be sort of a pain in the neck, but it probably would work okay. It becomes a washer, and that works okay. Works all right. But if you use the shell method, then your dy is your thickness here, and the y is going from C to D. Whatever you get your D is, that's what your limits need to be, C to D, okay? The shell, if this is your average height here, the P of Y, that's the radius of this rectangle that's going around there. This thing will form this cylinder with a hole in it, this pipe around that, and you sum up all those pipes from C to D, because you're doing your dy's. Okay? Consider the horizontal rectangle of width dy, delta y, that as the plane region is revolved around a line parallel to the x-axis. Okay, so they call that a line parallel to the x-axis. Okay. The rectangle generator represents the shell whose volume is the delta V of just this shell here is 2 pi times the radius of that, 2 pi r, times the height of that, the length of that, which is this one here. We have to have that as a function of y, okay? And we can figure out what that is times dy, okay? So what you would have to have is know the equation of this line as a function of y, not as a function of x, but as a function of y, and then subtract this end from it, and not as an x, but as a y here. But yeah, that's how you would do it. So this would be your delta V. Integrate that with a dx. You're always going to have the 2 pi out front, and then the radius times the height times your delta y. That gives you your volume dimensions. You can approximate the volume of solid by n such shells, the thickness delta y, height h of y sub I, and average radius p of y, okay, and the y sub I. And the volume of the solid, then they start with the summation, I is equal 1 to n. You're going to let n ultimately go to infinity down here, so we know where it's heading. 2 pi times the radius, that's going to give you circumference of that shell, times the height, that's the length of the shell, times delta y, that's the thickness of the shell. Okay? So bring the 2 pi out front, do this for n, I equal 1 to n, Each of these is the radius is a function of y, and the height, the length is a function of y times the dy. And then you approximate this, the approximation appears to become better and better as your norm, which is the maximum delta y that you have in there. The maximum delta y is going to 0, meaning your n is going to infinity. So then the summation becomes an integral. This summation becomes an integral. The limit as the norm goes to 0 of this thing will be 2 pi. The summation becomes an integral going from c to d. That's your limits on y, where you started this to where you ended it on y. P of y, that's the radius is a function of y, the height is a function of y times dy. Now, what that means, you have to know these two, okay, or be able to calculate them. That's going to be usually the biggest problem. The integral is the easy part, okay? Getting it in terms of y, or x if your shell is on that way. So to find the volume of a solid or revolution with the shell method, use one of the two formulas here. If you have a horizontal axis of revolution, then you're going to do dy's, because that's what's going around, okay? This is exactly backwards of how we did it with the disk method. If you had a horizontal axis of revolution, then you're doing either a disk or a washer. You did dx's, okay? Now we're doing dy's. And because you're doing dy's, your volume is going to be circumference, which is 2 pi times that radius as a function of y, times the length of it as a function of y, times your dy as the thickness, and that gives you that if you integrate from c to d. Now, if you have a vertical axis of rotation, you're doing the shell method, then it's 2 pi times your radius as a function of x, okay? Times the length as a function of x, times the thickness as a function of x. This is going from A to B. So here's the pictures that go along with that. What you need to know is what this curve is as a function of y, not a function of x. Okay? And then the length of this would be this is a function of y here minus this is a function of y. Okay? Your p of y would be this. That's the radius of revolution. And that needs to be expressed as a function of y, not of x. And of course your delta y here. And your y is going from c to d. The same shape if you revolved around the y-axis rather than the x-axis, or a line parallel to the y-axis, then you do this. You need to know this equation here as a function of x, and then your length is a function of x, your radius is a function of x, of course your dx here, and now you're going from x equal a to x equal b. You're going around that way. Should get the same answer. Well, no, wait, not necessarily, because you're going around different axes. But if these were the same, if that was symmetric, which it looks like it is, and these were the same, yeah, you should get pretty close to the same. It doesn't look like those are the same. It's like this is different. So don't expect them to be the same because you're doing different axes of rotation. So let's do one. Find the volume of a solid formed by revolving the region bounded by y is equal to x minus x cubed and the x-axis, from x going from 0 to 1, about the y-axis. Sort of a big boo hiss here, but let's see if we can do this. Let me get my pen set up. Okay. Let's make my... Oh, I was setting up my pen. There we go. Okay. Let that be my y-axis. And this will be my x-axis, because we're going around the y-axis. So here's your y, there's your x. Okay. Now, x is going from 0 to 1. Okay? So, don't know what y is yet, but let's plug in some values. When x equals 0, what's your y? Also 0. Okay, so there's 1 point. Okay? When x is equal to 1, what's your y? 0 also. I don't want to do too many in here, but let's just do something like maybe 1/2. What would your y be when x equal 1/2? Y would be 1/2 minus 1/8. So this would be 4/8 minus 1/8 would be 3/8. So if this is approximately 1 here, there would be a half, and there would be something like 3/8. So this point right here. Now, I don't know where it's going between that, but it's doing something bizarre. We could do something closer. Let's do 1/4 just to see what that gives us. Y is equal to 1/4 minus 1/64. Is that right? Is that right? Yeah. It's 4 times 4 is 16 times 4 is 64. No. Yeah, that's right. Okay. So this will be goodness, my brain's not working here. 4 will go into 64, 16 times. So that'd be 16 64ths minus that. That would be 15 64ths. And that's just less than one, a little bit more than one, no, less than 1/4. Right? So if this is 1/4 here, okay, so it's doing something like this. I don't know if that's accurate or not, but let's just say it's something like that. And we're revolving this around the x-axis, the y-axis, so this looks something like that as it revolves around here, okay? So you have a very flat bagel, right? Flat on this end and bagely on the other end, okay? Now, does anyone want to do a disk method on this? Please say no, okay? This would be a pain in the neck to figure, this kind of, that would be really miserable to do that disk from this side to this side. Let's not do a disk method, okay? So let's do instead a shell method. So your shell is going to be something like this. So we're going to have a dx here, okay? And what are we going to need to know? We're going to need to know I can tell you the height of this. The h as a function of x is going to be y minus 0, right? Because the bottom is 0. So that's just going to be x minus x cubed. That's the height of that thing. Now the radius here, they call it p, don't they? P of x is simply x, right? That's how far here you are out here. That's x, right? And your x is going from 0 to 1. So you're going to take this and revolve this around here, okay? So that's going to be the 2 pi times the radius. So your volume is going to be 2 pi times the integral from 0 to 1 of your radius, which is x, times your height, which is x minus x cubed, times your dx. Is that all there is? It sure seems like it. 2 pi x is going to be the circumference around here, and your height is going to be your length of that, which is this one 0. Okay, and then your dx is your thickness. Okay, so let's do it. What would you do first? Multiply, and you get, help me, x squared minus x to the 4th dx. Okay, that would be 2 pi. Now let's do the antiderivative. What does that give you? Help me. X cubed over 3 minus x to the 5th over 5, evaluated from 0 to 1. I think I can almost do this one. 2 pi. What would that come out being? 1/3 minus 1/5. I'll do the 0 part. Okay, done. And least common denominator here would be 2 pi times how many? What's the least common denominator? 15. How many 15ths is 1/3? 5 15ths minus how many 15ths is 1/5? 3 15ths. So that would be 4 pi over 15. There's the volume, I think. Let's see how the book did. Let's see if I can find it in the book. Yeah, there it is, 4 pi over 15. Good for them. Okay? Any questions on this? We'll show the way the book did it, which probably will be a little easier to follow, but you saw the steps, what you go through to get that, right? So less, and you did not want to use the disk method on that one. Believe me. I don't like using that anymore. Okay, never mind. All right. Because the axis of revolution is vertical, use a vertical representative rectangle. Since you're doing the shell method, that's what's going to come around. So there is the representative rectangle. Your radius here is how far you are from the x-axis, which is x, okay? Because it's from revolved around the y-axis, so that's going to be exactly that, okay? And your height here is going to be just what your function is, and your thickness is dx, which is a great thing to have as your variable here. Integration. You're going from 0 to 1. Now, I'm not sure my curve looked a lot like theirs, but it looked fairly similar. That's going around the y-axis. Okay? How's that? Blah, 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 blah. Okay? The distance from the center of the rectangle to the axis of revolution is your p of x equal to x. We said that. The height of that rectangle was just going to be from the x-axis to the curve. It's going to be x minus x cubed. And it ranges from 0 to 1 on x, because that was your integral. That's the thickness of your shell. Okay, so it's going to be 2 pi r. That's your radius, 2 pi p, which in this case is 2 pi x, times the h of x, which is that, okay, times dx. So the limit's going to be from, since you're going on x, 0 to 1. So that would be, the volume would be 2 pi of the integral from 0 to 1 of x times x minus x cubed dx. That's all there is to it. The calculus part is the easy part, okay? Why in the world they reverse the order, I don't know, but it's fine to do that. We said x squared minus x to the 4th. and they integrate that to be 2 pi times x to the 5th over 5 minus x to the 5th over 5 plus, excuse me, x cubed over 3 from 0 to 1, and that came up just like we had it, only we did 1/3 minus 1/5. They did minus 1/5 plus 1/3, that's fine, times 2 pi, and that gives 4 pi over 15, or 4/15 pi. Any questions? Just pretty much like we did it. Now, they're skipping example 2. How are we doing on time? We got some time. What's that?
16.
10 minutes? Yeah. Oh, more like 15, isn't it? I think so. Yes, let's not cheat ourselves at all. Okay. Example 2. Find the volume of the solid form by revolving the region bounded by the graph of x is equal to 3e to the minus y squared. Whew. And the y-axis, and you're going from 0 to 1 on the y-axis. We're revolving that around the x-axis. Okay. Oh, how I do not want to draw this shape, okay? Yuck. Okay. So let's do, you're revolving around the x-axis, so let's do the y-axis here, okay? We're going to do the x-axis here, and y is going from 0 to 1, okay? The shape that we're doing is there, okay? So we're given the formula x is equal to e to the minus y squared, okay? So let's plug in a y equal 1. What would your x be? X is equal to e to the minus 1. Something about 1/3, roughly, right? Plug it in, somebody. E to the minus 1.
Uh, 0.3678.
Okay. 0.6678?
0.36.
Oh, yeah, okay. I was thinking, okay, 3/6, a little bit greater than 1/3, okay? So let's just say it starts right here. And when we plug in y is equal to 0, of course, e to the 0 is? Yes, anything to the 0 is 1. So it does that, okay? Now, the shape of this is, I'm just going to copy it from the book. It's something like that. There's a little bit too much curvature in that, but something like that. And we're revolving this around the x-axis, okay? So, however you want to say that. So that goes from here to there. So this is what's going around the x-axis, okay? Now, you might say, isn't this set up well for a disk? I kind of think not, because this is a hard thing to integrate, okay? So let's not. So let's try a shell with it, okay? And the shell would be this length here, okay? That's what you're going around there. Now, so we've got a dy here. That's your increment. Your height here is here they, oh, I'm sorry. This is also included in this. So the base down here is just, that could be done with a disk method, but you don't need to. You can do this. So this is actually going, the height is going to here. It's not just to that part. I'm sorry, I misinterpreted. Okay, it's that whole area there under that curve. Okay, so your length of this, your h here, is exactly this curve here, e to the minus y squared. Now, I said that was a miserable thing to do, but hang on, it won't be quite as bad as we think, I don't think. Okay, what's your radius here? The radius here is just your y. So your p of y is just equal to y, just like we had before, okay? So now what we have is, this is where the beauty of this comes in, the volume is equal to 2 pi times that radius, that goes inside the radical, inside the integral, y times the height, or length of that, is e to the minus y squared, and the thickness is dy. Okay? Now you see why this works out much better. That y you have in there is part of a substitution. Yes, we can do that. If we were doing a dx and doing this to that, oh my word, that would be almost an impossible integral to do. Okay? Doing this. Now what is your y going from? 0 to 1. Okay? So the volume would be 2 pi. Now how are you going to do that integral? Hint. U substitution. Let u equal what? Say again? Not the e. The innermost part of the more complicated looking part. Yes, the negative y squared. Then du is equal to negative 2y, what else? dy. Perfect. Well, we don't have a negative 2y. We actually do have a 2y, just without the negative. So if we divide both sides of this by, pull that 2 back into there, and divide this by minus 1, okay? And you have negative du is equal to 2y dy. So now what we have, without the 2 there, we have the integral of minus the integral of pi times e to the u du, right? Because du is 2y dy with a minus sign. We got that out front. And you just got e to the u, right? We need to change the limits, don't we? So when y is equal to 0, what's u equal to? 0. And when y is equal to 1, what's u equal to? Negative 1. Oh, we don't like that, do we? How do we change that? You don't like going from the larger to the smaller. So what happens when we flip it? Yeah, it puts a negative on the outside, which makes that a positive. So that'll be pi times the integral from minus 1 to 0 of e to the u du. All right, I think I can almost do that integral. What is the antiderivative of e to the u du? please. That's one of my favorites of all time. Is what?
1
It's, yeah, 1 e to the u. Okay, it's e to the u. The derivative of e to the u is e to the u. The integral of e to the u is e to the u. I love it, okay? And this is going from -1 to 0. So let's do that. Pi times, what's e to the 0? 1 minus what? That was the upper limit. The lower limit would be
0.36.
e to the -1, right? And that would be whatever you were just saying. That's the answer, and they write it this way: pi times 1 minus 1 over e. You can write it that way too. It doesn't really matter. It comes out to be a number about 1.986. So almost 2. Okay. All right. That's the shell method. And I think we are awfully close to being out of time, aren't we? There's an exploration sort of in the middle of the page there, which is a little bizarre. See the advantage of using the shell method in example 2. Solve the equation x is equal to e to the minus y squared for y, and it is terrible. Then use that equation to find the volume using the desk method. You don't want to try it, okay, but you can try it if you'd like. All right, we'll pick up then next time with comparison of disk and shell methods, which is on page 467. Homework exercises here would be either 3 or 5. They're both at Calc Chat, and then any of the odds 7 through 11. They're all at Calc Chat, 7's at Calc View. Either 13 or 15, they're both at Calc Chat, or any of the odds 17 to 21, they're all at Calc View. I'm sorry, 17 to 21 are at Calc Chat, 17's at Calc View. 23 or 25, those are both at Calc Chat, 23's at Calc View, and we'll pick up with 27 next time when we do comparison of the two. Any questions? I'm afraid I've cheated you out of a couple minutes of your tuition dollars, but hopefully you'll forgive me, okay? Will you be kind to me, okay? Any questions? All right, I'll shut her down.